Our dynamic universe. The key areas covered will be projectiles and satellites, resolving the motion of a projectile with an initial velocity into horizontal and vertical components and their use in calculations, and comparison of projectiles with objects in freefall. What we will do today is quick revision of equations of motion, investigate projectiles, and relate the two above. Recap: resolution of a vector. We've looked at this before, but just a quick recap before we move on. Any vector x can be resolved into two components at right angles to each other. The horizontal component xh and the vertical component xv. This is shown in the diagram. The equations that we use are xv equals x sine theta and xh equals x cos theta. The vertical and horizontal components of a velocity vector v are respectively v vertical equals v sine theta and v horizontal equals v cos theta. Recap: equations of motion. The equations of motion are as follows: v equals u plus at, s equals ut plus a half at squared, v squared equals u squared plus 2as, and s equals a half u plus v t, where u is the initial velocity at a time of t equals 0, v is the final velocity at time t, a is the acceleration of the object, t is the time for the object to accelerate from u to v, and s is the displacement of the object in a time of t. The method for tackling problems is first writing down all of the symbols, second, filling in all your numbers and values given in the question. 3. If there are two directions, use this diagram for positive and negative values. If we're moving right or up, it's positive. If it's moving left or down, it's negative. And 4. Choose the best equation to suit the problem. Projectile motion. When an object is fired horizontally, it has both vertical and horizontal motion. For example, a cannon firing a cannonball. When a projectile is fired, it takes a curved path, as shown in our diagram just here. The projectile is launched with an initial horizontal velocity from an elevated position. This curved path is due to two things. 1. The horizontal motion, it's travelling at a constant velocity, and 2. The vertical motion, there's a constant acceleration due to gravity. These two motions can be represented in graphs. Here's the horizontal, and here is the vertical. The distance travelled is equal to the area under the graphs. So for horizontal, it's the base times the height, and for vertical, it's half base times height. In summary, the motion of a projectile consists of two independent parts or components. 1. Constant horizontal velocity, where acceleration is 0, and 2. Constant vertical acceleration caused by Earth's gravitational pull. These motions can be treated separately or in combination depending on the circumstances. Example 1. Horizontal projection. A projectile is fired horizontally off a cliff as shown. Find the time of flight, the range, the vertical velocity just before impact, the horizontal velocity just before impact, and the actual or resultant velocity just before the impact. First, let's write down what we know and what we don't know, splitting this up into our vertical and horizontal. So along our vertical, we know that our displacement is 45 meters. We know that our initial velocity is 0 because it's starting from rest. We don't know our final velocity. We know our acceleration is 9.8 meters per second squared. And we don't know the time. Along our horizontal, we don't know what our displacement is. We know that our speed is 5 meters per second. That's a constant speed there. And we don't know the time. The first question was asking us to work out the time it took for the ball to hit the ground. So we can use our vertical components to do this. So the best equation to use would be S equals ut plus a half at squared. Given that doesn't involve v, as we don't know v. So let's fill in our values. 45 equals 0 plus a half times 9.8 times t squared. Rearranging this, we get t equals 3.03 seconds. We can now add this onto what we know. So we've got 3.03 seconds here and on our horizontal. Because for both vertical and horizontal, the time will be the same. Part B was asking us to work out the range, so this is the horizontal distance. Because we now have the horizontal time, we can use speed distance time to work out this distance. So S equals Vt, S equals 5 times 3.03, and so we get a final range of 15.2 meters. Part C asked us to work out the vertical velocity just before impact. So we can use our vertical components this time. So the best equation to use would be V equals U plus AT. U was 0 here, A was 9.8, and we just worked out the time to be 3.03. This gives a velocity of 29.7 meters per second. Part D was asking for the horizontal velocity just before the ball reached the ground. This is actually going to be the same as our start velocity as it's constant. So our V is 5 meters per second. Part E was looking for the resultant velocity, so the actual velocity of the ball just before it hit the ground. For this, we want to draw a little diagram. We've got 5 meters per second in the horizontal distance, not horizontal distance, the horizontal velocity there, and the vertical velocity was 29.7 meters per second. This resultant velocity was where this dotted line is at an angle of theta. So to work out our resultant velocity here, we just use Pythagoras. So v squared equals 5 squared plus 29.7 squared. This gives an answer of V equaling 30.1 meters per second. We can use trigonometry to find out this angle here because we can't have a velocity without a direction. So we can say tan of theta is equal to 29.7 divided by 5. Rearranging this to give theta, we've got theta equals the inverse of tan of 29.7 divided by 5, which gives 80.4 degrees. So our final answer there is V is 30.1 meters per second at 80.4 degrees below the horizontal. We could quote that as 170 rather than saying 80 below the horizontal, so we're just adding 90 plus 80.4 there to get 170 rounded. An additional note on projectiles. For projectiles fired from the surface to a maximum height, 2 points must be noted. 1. The vertical velocity at the maximum height is 0 meters per second. 2. The time taken to reach the maximum height from a surface, t1, is equal to the time to return from the maximum height back to the surface, t2, i.e. the time taken to reach the maximum height is half of the total time taken. A golfer on an elevated tee hits a golf ball with an initial velocity of 35 meters per second at an angle of 40 degrees to the horizontal. The ball travels through the air and hits the ground at point R. Point R is 12 meters below the height of the tee, as shown. The effects of air resistance can be ignored. Calculate the horizontal component of the initial velocity of the ball, the vertical component of the initial velocity of the ball, and the time taken for the ball to reach its maximum height at point P. Let's start by drawing a small diagram of the initial velocity and the angle. We've got our initial velocity of 35 meters per second and an angle of 40 degrees. We can split this up into the horizontal and vertical component. And we know that our equations are the vertical component of the velocity equals v sine theta, and the horizontal component of the velocity equals v cos theta. Part 1 is asking us to calculate the horizontal component. So VH equals V cos theta, which equals 35 times cos of 40, which gives us an answer of 26.8 meters per second. Part 2 is asking for the vertical components of the initial velocity. So our vertical component of velocity is equal to V sine theta, which is equal to 35 times sine of 40 this time. And this gives us an answer of 22.5 meters per second. Part 3 is asking for the time taken for the ball to reach its maximum height at point P. So for this we want to look at our Suvat equations. So we don't know our displacement. We do know our start velocity, which is what we worked out here. That's going to be 22.5 meters per second. Our end velocity is going to be 0 because at point P is at the top of this arc that the ball's making. It's reached a vertical velocity of 0. Our acceleration is minus 9.8 meters per second squared because that's downwards. And our time is what we want to work out. So we have two unknowns, but we want to work out the time, so we can ignore the displacement. The best equation to use for this is V equals U plus AT. So filling in our numbers, we've got 0 equals 22.5 plus negative 9.8 times t. Rearranging this for t gives t equaling 2.30 seconds. Part B. From its maximum height at point P, the ball falls to point Q, which is at the same height as the t. It then takes a further 0.48 seconds to travel from Q until it hits the ground at R. Calculate the total horizontal distance travelled by the ball. We know that the horizontal velocity of the ball is 26.8 meters per second. We worked this out in Part A. We want to work out the horizontal distance d. And to do that, we want to use the speed distance time equation. However, we don't have the time just yet, but we can work that out quite simply. The time for the ball to reach point P from start was 2.3 seconds. The time it takes the ball from go to point P to point Q is also going to be 2.3 seconds, as these are identical. It's our curve there. And to get from Q to R, we've been told that that's 0.48 seconds. So our total time is going to be 2.3 plus 2.3 plus 0.48. This is 5.08 seconds. So we can add this on. 5.08 seconds. We now have enough values to work out our distance. So d equals vt. This equals 26.8 times by 5.08. So our total distance is 136 meters. A helicopter is descending vertically at a constant speed of 3 meters per second. A sandbag is released from the helicopter. The sandbag hits the ground 5 seconds later. What was the height of the helicopter above the ground at the time the sandbag was released? We are just working with the vertical components this time. We don't need to worry about the horizontal because the helicopter is descending. There's no horizontal movement there. So we can write down Suvat here. So what was the height of the helicopter? This is what we want to work out, our displacement. Our initial velocity, it says the helicopter was at a constant speed of 3 meters per second. We don't know our end velocity. The acceleration, 9.8 meters per second squared. In this case, the velocity was moving downwards, it was descending, and the acceleration also acts in the downwards. So we're saying that moving down is positive, just to avoid using too many negative values in the one equation. And the time this took is 5 seconds. The most appropriate equation to use for this would be S equals ut plus a half at squared. Substituting in our values, we get S equals 3 times 5 plus a half times 9.8 times 5 squared. This gives us an answer of S equals 137.5 meters, which corresponds to answer E. A stuntman on a motorcycle jumps a river which is 5.1 meters wide. He lands on the edge of the far bank, which is 2 meters lower than the bank from which he takes off. What is his minimum horizontal speed at takeoff? Let's look at what horizontal values we've got. We have a displacement of 5.1 meters. The velocity is what we want to work out. However, we do not have a time, but we can find this time using our vertical values. We have a vertical displacement of 2 meters. We have a start velocity of 0. We do not know our end velocity. We have an acceleration of 9.8 meters per second squared. Again, we're saying moving down is positive. And we have a time that we don't know, but the time is what we want to work out. So again, the most appropriate equation to use for this, ignoring v, is S equals a ut plus a half at squared. So 2 equals, this is going to be 0 because our u is 0, plus a half times 9.8 times t squared. Therefore, rearranging this, our t squared is equal to 0.408 and so on, so t is equal to the square root of this, which is 0.64 seconds. We can then use this time, 0.64 seconds, to work out the velocity horizontally. So S equals Vt, 5.1 equals V times 0.64, and rearranging this for V gives a value of 8.0 meters per second. This corresponds to answer D. A javelin is thrown at 60 degrees to the horizontal with a speed of 20 meters per second. The javelin is in flight for 3.5 seconds and air resistance is negligible. What is the horizontal distance that the javelin travels? First, let's write down what we have horizontally. We have an unknown displacement, an unknown velocity, and a time of 3.5 seconds. This displacement is what we want to work out, and we can find out the speed by splitting up this 20 meters per second into the horizontal and vertical components. So if we draw a small diagram of this, we have our 20 meters per second. We have our horizontal velocity and our vertical velocity. We know that our horizontal velocity is equal to v cos of theta, and we have 60 degrees in there. So this is equal to 20 times cos of 60, which is equal to 10 meters per second. We can put this into the values that we know now and use this to work out our horizontal distance. So S equals Vt, which equals 10 times 3.5, which equals 35 meters. This corresponds to answer A. Satellite motion. Satellite motion is an extension of projectile motion. Here we can see we've got the Earth and satellites moving around the Earth. Satellites are constantly falling towards the Earth in orbit. They remain in orbit and do not move closer to the Earth because they have great enough horizontal speed. They do not move off into space because there is a force of gravity holding them towards the center of the Earth. How can a satellite be accelerating when it is traveling at a constant speed? A satellite has constantly changing velocity because the direction is constantly changing, and this means that a satellite can be accelerating when it has a constant speed.